This video I want to show you how to derive by using complex calculus a result that is not so straightforward, and it's an integral from minus infinity to plus infinity of the cosine of t squared dt. We will show that this is equal to integral from minus infinity to plus infinity of the sine of t squared dt, and this is also equal to the square root of pi over 2, like this. And we will show it first by using just an informal way, an informal derivation. And then I want to justify the result by using complex calculus. We will start from the following integral, and we will assume this to be given. So integral from minus infinity to plus infinity of e to the minus x squared dx. This is equal to the square root of pi. It's a nice exercise, for example, in multivariable calculus, so I'm assuming that this is well known. And then what I'm going to do first is to use the following substitution. X equal to I, in particular the square root of I, times y outside of the square root. So this substitution should be justified according to the theorems that we saw in complex calculus. But first, let's just assume that we can make this substitution, for example, also in multivariable calculus or in single variable calculus. Why not? And if we make this substitution, we have integral, and then here we have e to the minus I y squared, and here we can rewrite this as dy times the square root of I. And the integral starts at minus infinity, and it goes all the way up to infinity, because the variable x is represented by square root of I times y. So the differential of this is equal to the differential of x, and it makes sense to consider the integral from minus infinity to infinity. And this should be still equal to the square root of pi. So you have to be careful here, because in general, when you are adding to a variable of integration something which depends on a complex variable, well, we should consider complex calculus. But we will show rigorously that this is actually a correct result. So from here, what I'm going to do is I'm going to rewrite this integral. So the square root of I can also be written as the square root of e to the I pi over 2, which is equal to e to the I pi over 4, which is equal to 1 over the square root of 2 plus I over square root of 2. Now, you can multiply both sides of this equation by the complex conjugate of this, and what you get is integral from minus infinity to plus infinity e to the minus I y squared dy equal to square root of pi times 1 over square root of 2 minus I over square root of 2. Now if you rewrite this complex exponential as the cosine of y squared plus sine of y squared times minus I, so here you have I, and then we have to put a minus here. Well, now if you do the algebra, you will get exactly this result here. So you simply have to take the real part of this and then the imaginary part, and then you can merge the two equations that you get, and you will simply get this result. But now we really need to justify a little bit more rigorously this substitution. In general, this is okay, this can be done with some kind of intuition, but we should justify it. And in particular, we will consider complex integration. So we will consider a contour. Let's assume that this horizontal line is the real axis, and then this vertical line is the imaginary axis. Then we will consider the following curve, the following contour. We are moving along the x-axis. Then let's assume that this distance from the origin is capital R, and then we are spanning along a circumference here, and this angle is pi over 4. Then, so we are moving like this. Then we are moving like this in the third quadrant, and then we are closing our contour with another portion of circumference like this. So this angle here is of course pi over 4. This is the contour that we consider. And as you might imagine, we will let capital R go to infinity. And we will have to show that the integral along these portions of circumference will vanish when we let capital R go to infinity. So um, I want to show it, but first we need to consider a complex function to integrate along this contour. So we are integrating over that closed contour, and we are integrating the function e to the minus z squared dz. Since this function is continuous and it doesn't have any pole inside this contour, this integral will be equal to 0 according to the well-known theorems of complex calculus. So I'm going to call the horizontal line gamma 1, then we have gamma 2, this portion of semicircumference, then we have gamma 3, this slanted line here, this line, and then we have gamma 4, the other portion of semicircumference. Well, the integral over gamma 1, when we let capital R go to infinity, will give us simply the integral from minus infinity to plus infinity of e to the minus x squared dx. That's very easy to see. Then what about the integral over gamma 2? Well, the integral over gamma 2 is an integral from 0 to pi over 4. If we make the substitution z equal to capital R e to the I theta, and this will give us e to the minus r squared e to the 2I theta, and then we have I r e to the I theta d theta, and then this can be written as e to the minus r squared cosine of 2 theta e to the minus I r squared sine of 2 theta. When we let capital R go to infinity, we see that this term will make everything vanish because it's decaying exponentially. We have this capital R which goes to infinity, but this term here will definitely prevail over capital R. And this is just the intuition. Of course, you can do it more rigorously because in principle, you should take the real part, the imaginary part, and see what happens to both of them. But you can see quite easily that they will both vanish. And then we have also the integral over gamma 4, which is very similar to this one. So in that case, we are integrating from this point here, and then we are moving like this, so clockwise along this semicircumference. Sorry, not a semicircumference, just portion of circumference. And then we can rewrite the integral like this. For example, we can integrate from pi plus pi over 4, and then we go to pi. So this angle here, we are integrating from this angle here, which is pi plus pi over 4, to this angle here, which is pi. And then, of course, the integrand can be written exactly in the same manner as we did here. So we simply have to rewrite the integrand like that. But when we let capital R go to infinity, we see that this integral will also go to 0, just like this one. And then finally, we have the integral over gamma 3, which is the integral along this line, this slanted line here, which makes an angle of pi over 4 with respect to the horizontal line. And therefore, it's quite easy to see that this will be an integral. So we have to parameterize our line, and in particular, in that case, z will be equal to a parameter t times e to the I pi over 4. So this is the phase of the complex number, whereas this is the mode, t. But t varies because we are moving on this line. In particular, for example, if we consider this point, the mode will be t, So this is t, which is positive, and then the phase will be e to the I pi over 4. Whereas if we consider a point here, this point here can be written like this. So the mode of that will be the mode of t, and if we assume t to be positive, this is just t times e to the I, and then we have to consider this angle here, which is pi over 4 plus pi. So this is equal to t times e to the I pi over 4 times e to the I pi, which is minus 1. So we get minus t, like this, right? So in principle, we can just simply consider the following parameterization. We can consider z to be equal to t times e to the I pi over 4. And then we know that when t is negative, so in particular here, because in this case, here we were just considering t to be positive because we were considering the mode, right? So I should put these bars. But if we want to be more general, we can simply parameterize our curve, our line. In this case, it's not a curve, it's just a line, like this, but t will go from minus infinity to plus infinity, because it can also be negative. And if we assume it to be negative, you can see that it describes perfectly well also the points on this part of the line in the third quadrant, as well as the points on the first quadrant. So I hope you understand the intuition. You can simply think about it and it's quite easy to understand. But if it's the first time, of course, you might need more time to understand it. There is no problem. So you should not feel scared by this, of course. You should be familiar with this. So from here, we can substitute this formula, and we have e to the minus z squared, if you remember. So here we have e to the minus t squared, and then here you have e to the 2I pi over 4. So you get e to the I pi over 2, like this. And then you have the differential of t, and this multiplies e to the I pi over 4. But what is e to the I pi over 2? Well, this is just equal to I. It's just equal to I, and of course, as I've told you, we have to integrate, in this case, from this point. And remember that r goes to infinity, so we have to integrate from infinity to minus infinity, like this. So by using the theorem of residues, we know that the integral from minus infinity to plus infinity, e to the minus x squared dx, which was the integral over gamma 1, should be equal to minus this integral here. So you can rewrite this as plus minus infinity to infinity e to the minus I t squared dt, and then you multiply this by e to the I pi over 4. So this is one way to simply show that what we did at the beginning was actually correct. So in particular, in that case, we made the following substitution, this substitution here, and you can see that it led us to the correct result, which was this one, but instead of writing square root of I, we have to write e to the I pi over 4. So the correct result actually is this one here.